So when we're talking about dilations, we're talking about something that you've actually already done before. The difference here is we are going to be dilating a figure on a coordinate plane. So that is going to be the big difference. Notice how we have shapes that are on grids, right? Which is a coordinate plane. When have you dealt with dilations in the past? Levi? The mug-wump things, when you had to find the gate crashers who were imposters to the Wump family who wanted to just eat their food and drink their drinks. Yes? You had some dilations on Delta Math that you definitely did. Any other times? Scale factor. So dilation factors are going to be the same thing essentially as a dilation factor. So scale factor, dilation factor, more or less synonyms. And before we really learn about how to make these figures get bigger or smaller, when in real life have you seen dilations? When does a dilation happen normally when you're just in your day-to-day life? Caden?
Like if some like restaurants have like glowing signs that grow and shrink with the lights.
Okay. Yeah, so they have advertisements that get bigger and smaller to try to draw your eye to it. That is absolutely a dilation. Any other ideas? Alexa?
Maybe just like different sizes of anything around your house, like you don't have to dilate that. Like if it just say like a bag of chips or something, you might have like a big bag of chips and a smaller bag of chips.
Okay, so you'll see grocery store items get bigger or smaller, and don't you hate it when the bag of chip is like gigantic and then only about a quarter of it is full? Yes, Levi?
When you're like shopping and you have like 3XL t-shirts and then like 2XL shirts, it's like shrinking a lot and expanding a lot.
Okay, garments. So yes, the scaling up, scaling it down. Yes?
Your pupils dilate.
Oh, pupils. So right now, the room is fairly dark, so your pupils will be larger. If we turned on all of the lights, what are going to happen to your pupils? They're going to shrink. They're going to get smaller. During your recreation time, when do you see dilations? When you're hanging out with your friends in particular? Is there a time that you see dilations in graphics? Yes?
In video games, when you get further away, things shrink.
Oh, video games. And you said when you. So what perspective video games are we talking about? So first-person video games are using dilations to make it look like you're actually in the world. And when those zombies come after you, and they're running right at your face, right at your face, that's a dilation. So we deal with dilations frequently when you look at images on a screen. That's what makes it look realistic, like you're actually in the world that you are looking at. VR goggles in particular are dealing with dilations, because that makes you feel like you're in the location that you're looking at, right? All right, so that's what we're talking about today. And so when we have a dilation, we have to have a point of dilation or a center of dilation. And so the point or center of dilation is the point where the dilation originates from. Now, in first-person video games, that center of dilation is actually it's called the vanishing point. And the vanishing point is on the horizon line. So that's what we're talking about in video games. So a dilation factor is essentially going to be a scale factor. And if you have a dilation factor that is greater than 1, will you have a larger or a smaller figure? It's going to get larger. If you have a dilation factor that is between 1 and 0, what will happen to your figure? It will shrink. And it's actually possible to have a dilation factor that is less than 0. Oh my gosh. Struggles are real today. So if your dilation factor is less than 0, or 0 is greater than your dilation factor, it's actually going to look like that figure is getting pulled in and shot out the back, and it's going to flip. That actually occurs in your eyes. So whether you realize it or not, the image on the back of your retina is actually flipped around, and then your brain puts it right side right. So that's what we need to have in order for us to perform a dilation. So let's take a look at our first problem. We're going to dilate the triangle. Now, the triangle is not as exciting as a zombie, but it is going to be easier for us to manually enlarge it, so we're going to go with it. So we are going to dilate the figure in the upper right, and we're going to have a dilation point, or center of dilation, at -7, -7. And we're going to use a scale factor or a dilation factor of 2. So my first step is to go ahead and let's locate that point on the grid. So go ahead and put a dot at -7, -7. And then from that dilation point, we're going to draw some construction lines from the dilation, from the center of dilation through the vertice to the end of the grid. Now, please use don't look at me like I'm crazy, Abby. Trust me on this one. And we're going to use a straight edge. A ruler is great, but it doesn't have to be a ruler. It just has to be a... Okay, we can fix that. So we're just going to go ahead and draw it through. And a straight edge is going to be great. And let's do that for all of the vertices. All right, so now we are going to measure the vertical and the horizontal change of each vertice from the center of dilation. So in other words, if I use the center of dilation, how far over and how far up did I go? So from this point here to this point here, how far did I go? I went -1. I went 1 in the negative direction. How far up did I go? This one is positive because up is a positive, down is negative. All right, and we are going to apply a factor of 2. So we're going to multiply each of these by 2. So what is -1 times 2? So instead of moving 1 in the negative direction, I'm going to now move 2 in the negative direction. Instead of moving 5 in the positive direction, I'm going to move 10. So from the center of dilation, I'm going to go to the left 2 and up 10. Oh my goodness! Look at that! That point is on the projection line. No way! Isn't that cool? It's amazing. The crowd goes wild. There's no energy here. Woo-hoo. All right, so then I will do the exact same thing for each of my other points. So if I'm looking at this vertice right here, how far over, how far up did I go? From the center of dilation, how far over did I go? I heard someone say, went over 1, up 2. So now what will I do with this? Multiply by 2. So 1 times 2 is 2. 2 times 2 is 4. Oh my goodness. That's also on the projection line. So much fun. All right, and then finally for our last point, how far over, how far up? And 5 over. So I'll multiply both of those by 2, and I will get
10 over 4.
Oh my goodness, that's on the projection line. And now we just connect the points. Now, a little hint on knowing that you are right. So I'll use red. So when I draw this line here, it should be parallel with this original line as well. So my lines should always be parallel to the originals. And does it look like my triangle is being shot out of that point? No. What?
Oh, yeah.
It definitely looks like that triangle is originating from the center of dilation and getting... Yep. And there we have a dilation. It is kind of cool. So here's what I would like you to do. I would like you to please do the next two. But before I go ahead and say do the next two, I do want to call your attention to two things. First, we're doing a reflection over the line x equals 2. X equals 2. Well, where are all the x values equal to 2? Is it a vertical line or a horizontal line?
No,
Why would it be vertical?
there's only, it's 2 is a single point on the x-axis, which is
On the x-axis, because x equals 2, and then all of the points on this line would have an x value of 2. Okay. So with that in mind, I would like you to please try the next two problems, and this one will have a dilation factor of 2 as well. All right, go to it.